Did you get my email yesterday with the link to the hangout?
No.
That I sent to DG and DRUG?
Oh, probably.
There's a link in there. You can follow that. Did you go on the Grand Canyon trip?
Yeah.
This year?
Yeah.
Nice.
It was awesome.
Did you do the top half or the bottom half?
Top half.
Nice. I did the bottom half last year.
Oh, you did? Yeah. It's pretty sweet.
That's fantastic.
Yeah.
So, yeah, how that.
Little by little.
God.
How do you join that?
Are you going to watch? But I don't watch that.
You present.
Yeah.
Um,
Can you invite me?
yes.
Regarding land coding and stuff.
I just sent an invite. See what that does. Did that send you an email?
Yeah. Yes. Okay.
Okay, so click join.
I did. That's me.
Maybe click join again. Cool. And now I'm gonna broadcast you. I'm gonna mute my video.
Whoa.
And you are live recursively on the
So scary. Okay. How do I share my screen?
Yeah, how do you share your screen?
Screen share. Okay. Hold on. I've got it. I wonder should I do. I don't know how I'm gonna do this. I guess I'll just do the entire screen because. Oh my god, no. Stop. Please stop. Okay. All right, I'll just do. I'll try to do between the two. Maybe that'll work. Is that showing up on?
It is.
Okay. Yeah. Well, I don't know how we're gonna do this.
Let's give people a minute or two to show up.
Yeah. I want to go back and forth between these two because they're kind of visual. Yeah, but we'll figure it out. I think.
So sharing your screen shouldn't do that infinite regress thing. I'm not sure why that happened.
You know, here.
Oh, it's because you were viewing.
Yeah, I'm sure if I actually. If I do.
Video.
Well then.
Well, but that was on a video, so go back to that hangout.
Well, so what do you see though if I just had this? Can you just see my screen now?
No. Well, actually, your face on the screen, which is nice.
Oh,
but
that's weird.
let's go back to that page. Let's see if we can just share the whole screen.
Screen shared and then hide it.
you see that?
When she put,
Yeah, it opened and then in the background it opened.
So let's try entire
Little
screen. And then minimize that window. Yeah, cool. So now we see your whole computer. That's good.
Great. Okay.
Let's give people another minute or two to show up because I need to use the bathroom. We'll get going.
See ya. I don't know what that looks like. So weird. Okay. Good.
Go set.
Yeah.
Cool.
Okay. So, I'm Grace. I'm a third year in Truman Young's lab. Honestly, the amount of experience I have with structural equation models is like medium, but that's okay. Do you all know what structural equation models are? They're basically just kind of like networks of equations that you can use to describe your system. And they're really useful because one, they're kind of visual, and two, I think they're closer to how we actually like often think about ecological systems. So we often think about A affecting B, B affecting C, C like looping back and affecting A in some other way. And you can get at that with ANOVAs and regressions, but often what you want to test is kind of like these network hypotheses, like what is your hypothesis about how a whole system works? And structural equation models are a great way to do that. So there are a lot of good resources out there that will take you through the basics of structural equation models. Jim Grace from USGS has probably the best website out there for introduction to structural equation models. He goes through all the basics, and he's still building it, so a lot of the code is not there yet, but I think it will be, and it's a really great resource. And then the package I'll be showing today, Lavaan, also has some good tutorials with example code, and I think Lavaan is probably the easiest package out there to do structural equation models in right now. There are a few others that you can use, and if you want to use Bayesian, you can program in WinBugs, or there's kind of proprietary software out there, which I'm not going to get into. And Jarrett Burns at UBC also has a website set up for structural equation models, which goes through a lot. So yeah, why structural equation models? They're good for testing complex hypotheses, like I said, and alternative hypotheses. And so they're typically multiple equations and kind of represent these like network hypotheses. So you can test both direct and indirect interactions in your data. And kind of the nice thing about it is you can have variables that are at the same time predictors and response variables within the same set of equations, which is kind of probably how you think about your data a lot of the time anyways. Just a little side note on sample size, because often we have really low samples. This is taken from a workshop I took at ESA with Jim Grace. Basically, you're gonna need at least 5 samples per parameter at very least. So a parameter is kind of like, you can think of it as like one of the paths you're gonna draw at like its very basic form. So the more arrows you're drawing, the more inferences you're making in the data, the higher your sample set needs to be. The more samples, the better. It's kind of an interesting thing. Like you could have a data set with very few data points, and you could put it in, write all your equations, run it in R, and you'll still get answers. So like you really have to like use your own discretion here, because R will spit out answers at you. It's just like you might not necessarily want to use them. They might not actually be valid if you have a really small sample size. So keep that in mind. You can also do all these really cool things with structural equation models. So you can do like latent variables. So you can have something, say like performance, and performance might actually determine 5 downstream things. And those 5 observed responses might all be correlated with performance, like differences in performance. So you can kind of like package them together and basically tell your structural equation model that there are correlations between variables that are all based on one kind of driving factor, like fitness, performance, that kind of thing. Here's just like another way of thinking about it. So like if you have stress is related to fitness, what you might actually be measuring is some stress indicator and then 3 traits of fitness, but what you're like actually thinking about is stress and fitness. Okay, so I'll show you some R code for this. So like I said, I think the easiest way to do structural equation models So the easiest package out there right now is Lavaan, definitely. There are a few others. There's one built into our SE that you can use, and I think there's one called M+, but Lavaan is like by and far the easiest and most intuitive. So I would recommend using it. There's also this kind of supplementary package QGraph, which can work with Lavaan to show you pretty diagrams of your data. Honestly, it's probably easier to make your own diagrams in PowerPoint, but you could use this to kind of specify.
Could you zoom in a little bit there, or just do the like hit Apple plus or something? That blows up a little. Thanks.
Yeah, no problem.
Would you say that viewing package was?
QGraph, this one, yeah. So this is a built-in data set that I'm going to show you, so you can try this on your own too. And the variables are not very descriptive what it is, but it's looking at all these different indicators of democracy, I think. I don't really know what this data set is, but it's great for showing you kind of the capabilities of Lavaan. So here's an example model that we can build. So this in Lavaan, you can specify different kind of types of relationships using tildes and equal signs and double tildes. So these first 3, the equal sign tilde, those are latent variables, which I showed you. So it's saying that x1, x2, and x3 are all intercorrelated and related to some measure here at ND60. Sorry, this is terribly non-descriptive. And same with these y's. And so these three variables, in60, dem60, and dem65, are not actually in the data set, the original data set. They're kind of like these composites of the variables, the x1, x2, and x3. And what you're interested in is kind of like these relationships. So it's like, say you're interested in stress on fitness, but like what you had for stress was like cortisol levels and whatever else, like time spent avoiding predators, that kind of thing. You could add those and use them as a latent variable for stress, if that makes sense.
So are you defining in60 and dem60 there?
Yeah, so you're basically, you're defining them based on these variables is kind of like how you can think about it, sure. Yeah, that's a good way to put it. So you can think of in60 as some composite of x1, x2, and x3. Dem60 as those ones, dem65 as those four. So tildes in Lavaan are just like regressions you would do otherwise. So you're saying this is your response variable, this is your independent variable, and same with this. So what this would look like, I'll show you after I run, because I can show you here. It's basically saying dem60 is dependent on in60, and then dem65 is dependent on those two. So you kind of get this like triangle. Sorry, I should just visualize this. And then you can do correlations between variables. So in this data set, I think the different like y1 and y5 are the same measure taken in different years, for example. And same with y2, y4, and y6. So this plus sign here, you can also write this on two separate lines as like that. It's just kind of shorthand. And so that's saying that your variables are somehow correlated beyond just what you would think. Like there's a correlation going on there. And so you create these models, and you can create alternative models too. And you put them in as this. And then you can fit them using Lavaan. So the function is just SEM, and then your model that you've specified here, and your data. And so once you fit it, you can get a summary of your fit. I'll go up. Oh, okay, so these outputs are kind of complicated, but we'll go through it. So the first part of it, so it converged normally after 68 iterations. That's good. You want your models to converge. If they don't converge, then something's not right. Then your data is not really fitting the model. You get maximum likelihood estimate. Degrees of freedom is your leftover degrees of freedom. So if you had a totally saturated model, so if you thought of every possible pathway between all your variables, then that would be 0, and that would mean that it has everything in there, which would also mean you'd need a ton of data to do, because you need a lot of samples for all your degrees of freedom. So this p-value, this is actually kind of counterintuitive. You want this to be above 0.05. If you have a low p-value, it means that you're rejecting your null hypothesis. But the null hypothesis actually for these models is that the data fits to your model. So if you reject your null hypothesis, you're basically rejecting the idea that your data and your model fit. So low p-values are bad. It means your data doesn't really fit your model. Which, yeah, is like something you would not expect and something that is like actually, I don't know. When I was first looking around at this, I like did not realize that that was like higher p-values are a good thing in this case and was really confused. I was like, oh, but that's fine. You can then go down and look at your estimates, z-scores, p-values for your different correlations between variables. I added in this statement here, r squared equals true, so that you could get the estimates of your r squared for each variable that you estimated. So this is, I think they have this data set built in because it has really high r squared values. There's a lot of prediction power going on. So this is from QGraph, this line SEM paths. And what it'll do is kind of visualize your data set, or not. Oh, how did you do that?
And standardized is just telling you to standardize the data.
Yeah, standardized, yeah, just standardized data. And this didn't really come out. And
Run that line again.
okay, well that's okay. You can see it in the corner. Basically, it'll give you coefficients between variables and error coefficients, and SEM paths also will adjust thickness for the strength of the relationship. So higher coefficients will get thicker lines. Green is positive, so this whole data set is green, which is fine. If you had negative relationships, SEM paths will put it in red for you. You can specify colors and that kind of thing, which is nice. Yeah.
Dash lines like indirect.
Yeah. So sometimes you'll get p-values up here that are really low, and that kind of suggests that there's something you're missing from your data set. And there's this function in Lavaan called mod indices, and basically what it does is creates a kind of correlation table for you. And you'll go through, and if there's something like really egregious that you've missed, which is not the case in this data set, what will happen is this mod indices value will be really high. And then you can think about that relationship and whether or not you'd want to add it into your data set and whether it makes sense biologically based on your data.
Could you repeat that?
Yeah, so this function mod indices basically will tell you whether or not you're missing something big from your data set. So it looks at all the possible paths given your data and basically looks for really significant correlations that you might have missed, that you might not have specified or thought of
Oh, so missing like pathways in the model.
Mm-hmm.
Oh, okay.
Yeah.
What's really big? Like 4 is big or like 1,000?
It'll be like 40. It'll be like pretty big, like orders of magnitude bigger. Yeah, and yeah, you can just go based on to like the biggest value would be a good place to start if you're not getting a model that fits pretty poorly. There's also a function to look at like variance in your different variables. Lavaan doesn't like it if you have like really big differences between variance in your data set. It'll still run and give you, I mean, so it'll tell you to scale your variables to have similar variance. I honestly am not really sure why, because you still get the same answers, but it's something that it doesn't like, and it'll spit out this warning message. So if that happens and you don't like that warning message, you can just rescale your variables so that it goes away. But for like these linear models, it shouldn't make a difference. Yeah, unless you guys can think of a reason why it would make a difference.
Well, I assume this model is doing some sort of, it's solving with some sort of parametric test.
Mm-hmm.
Right?
Yep.
So in that case, you need your residuals to be independent of your mean. And if some of your values have way higher variances and way larger means than others, the model might be detecting a correlation between variance and means. But I'm just making shit up here. Yeah,
that seems reasonable. I mean, like in my experience, it hasn't really altered any response that I've gotten. So take it or leave it. You can rescale if you'd like and see if that changes anything. You can also, on these models, you can use AIC, BIC, whatever you want to compare models, which is really useful. So I made a second model where I just took out one of the predictor variables in the regression. And then you can use AIC just like you'd use it in regressions or whatever other models to compare different model fits.
Chris, can you apple flush again?
Oh, sorry. Yeah. Yeah. Okay. You can also add in like nonlinear data. So if you think your data might be nonlinear, you can add in terms for nonlinearity. So this is a data set of fire severity and tree richness and cover that, I forget which paper it's from. But if you, for example, thought there might be some effect of like cover squared on your data, you can also add that into your model. So these two examples, this one is just cover impacts richness and fire severity impacts cover. Both kind of statements that seem reasonable. And the second one, you can create a variable for cover squared to try to get at kind of this, if you think it's a nonlinear quadratic relationship, you can add that in. And then you might want to, so, okay, this is the error you would get. So some of the variances are at least a factor 1,000 times larger than others. and then you can see which ones these are using Airtable. So if you do that, you'll see richness has this huge variance here, 228 versus like 0.1 and 2. So you could scale that, rerun your models, which are now happier, and then look at your different models. And if you do, you'll notice, like, for example, in this one, there is some significant effect of cover squared on richness. So it's just a way of incorporating in nonlinearity in your data. Yeah, so there are a lot of other things that, yeah, okay. We kind of went through this.
So does that SEM pass function come directly from QGraph, or is that from the SEM plot?
I thought it was from QGraph, but I might have just, is it actually coming from another thing?
I don't know. It doesn't seem to be in the QGraph that I downloaded.
Okay, I might have just have another, sorry.
Because there's something called SEM pass that seems to be the right thing from the SEM plot library.
Okay, yeah, I know one of the packages is kind of like deprecated. I might have just added the wrong one. Sorry. We already went through that. Structural equation models can also do all these other things. So there are these like composite variables, which like you can say like one variable is a composite of information from 2 or 3 different variables. You can do time series. You can do kind of Bayesian approaches, which are harder to do. You can't do in Lavaan. You'd have to do it in WinBugs, that kind of thing, which I don't know how to do, but you can do it. There's code out there. There's also a package called Amos, which would do Bayesian for you. It's really expensive. I've not tried it. Yeah, it's like thousands of dollars, I think, at last check. Yeah, it's a package on top of SPSS, right? Yeah, yeah. You can also do things like spatial autocorrelation, and the way this got explained to me is spatial autocorrelation. Basically, you adjust your sample size based on the amount of spatial autocorrelation that you detect, and you can do that based on like a Moran's eye or something like that, like quantifying the amount of autocorrelation you have and then adjusting your sample size based on that. And I linked, I'll send this out to a paper that did that and can go through the methods. Yeah, so that's kind of just like an intro to it. Sorry, I can't give you more information, but like Lavaan is a great place to start. And it's a great way to kind of like think about relationships between variables and start building like network hypotheses and alternative hypotheses and testing them. Yeah, and Jim Grace has a lot of great information on his website for like delving deeper into more intricate kind of problems. Yeah.
Do you have any thoughts on like some of the pitfalls you fell into when you first started messing with these SEMs?
Yeah, so I think like the sample size thing is definitely a pitfall because at least for me, I would like to create pretty complicated models, and the data I have, like the amount of data I have just like really doesn't allow that, but you wouldn't actually know that based on your output from your models. Like it would tell you that your model converged and it's great and everything's happy and all these things correlate, but like really it's probably totally overfitted and not actually appropriate for sample size. So that's definitely something you should keep in mind when you do it. Just like the output itself is kind of hard to interpret at first. Spend a lot of time kind of like thinking about that and what it actually means. And like the tutorials out there are really great for kind of like going through that and telling you what things mean. And also like another pitfall, I think, is that people like to use structural equation models to kind of like assert some causality in a system. And really what you should be using it for is like thinking about network hypotheses and why one might be better than another, and that kind of thing. I don't know, people are really uncomfortable with asserting like causality based on structural equation models, that kind of thing. People do it a lot, but doesn't mean you should. I don't know, but like the syntax of Lavaan is pretty easy to use, at least for kind of like basic starting out models, regressions and autocorrelations and that kind of thing, which is really nice. You can definitely like shoot out a bunch of pretty simple models pretty quickly and compare them.
Do you want to pull up that plot and show us what that says?
Yeah.
Are those R squared numbers?
So those are, they're not, well, they're correlations. They're not, why don't you work?
Oh, you should do 3 like variables.
Mm-hmm. Yeah, so maybe I should do it on the screen. So for example, like, yeah, there's D60, D65, and I60. And they're latent variables. And the idea is, like, for example, for D60, you have Y2, Y1, 2, 3, and 4 that are all autocorrelated and related to changes in D60. And same with D65 and I60. And you've got relationships between these 3 variables. So the strongest relationship is here. The strongest correlation is between D60 and D65. And then you've got some kind of weaker correlations.
Is that what that horseshoe means?
Those are error variants, I believe. These.
Yeah, like that one, and then the one under the I60.
So I'm not entirely sure actually, but I'm pretty sure they're a measure of error variance. But I can't give you a better answer. I'm sorry. Yeah. So they're a cool tool.
Can you show your tutorial slide?
And we'll put this up on the website.
Wait, which? This one?
The link slide.
So what have you been using these for? Do you measure a bunch of physical variables and have multiple biological responses? Or what?
Yeah, so I've been looking at effects of large herbivores on densities of termites. And so there's this effect of large herbivores on termite density, and there's also an effect of tree density on termite mound density, but there's also this relationship between large herbivores and trees because large herbivores like to knock down trees. So you get this system, this basic system where you have trees or large herbivores negatively affecting trees, trees positively affecting termite mounds, and termite mounds. Wait, there's one more link. Oh, there's also
affected by it.
yeah, there's also this adaptive gradient that affects tree density as well. So it's kind of like looking at that system, and the ultimate goal is to look at what is impacting downstream the density of termite mounds. Yeah, so it's like multiple steps to get there, which is nice. And it's nice to visualize it that way too. Yeah. Cool.
Thanks, Chris.
Yeah.
Yeah, thanks a lot.
Whoa.